Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about the solid mechanics and material subject. So in this subject already we have discussed about simple stress and strains and shear push and bending moment diagrams. And previous session we have discussed about the bending stresses and shear stress distribution in various beams. So in this today's topic, slope and deflection of beams. So we will see what do you mean by slope and what do you mean by deflection? What is the importance of slope and deflection? Deflection, these two terms in beams, and how to calculate the slope and deflection of different beams. We will see in this session. So before going to the main topic, the student should be able to utilize the Maxwell's reciprocal theorem, double integration method, and the moment of area method for determining. They should know. So this is outcome of this module. So Maxwell's reciprocal theorem we will discuss later, and double integration method also we will discuss. And present in this today's session, we will see the slope and deflection part of the beams, various the slope and deflection definitions, and then how to calculate the slope and deflection of beams. The derivation part we will discuss in this topic, in this session. So first of all, what do you mean by slope? So it is the angular shift at any point of the beam between no load condition and loaded beam. So in the angular shift at any point of the beam between no load condition and loaded beam condition. So whenever the beam is subject to load or no load. So its value is different at different points on the length of the beam. So suppose you take the cantilever beam. Whenever this is subjected to load, the deflection like this. So in this, so what is the slope and what is the deflection? So it means it is underloaded. So it value is different at different points of the length of the beam. Here one value will get, and then one more, and another like this. So it is represented by I or theta, that is slope. Its units are radians. Theta units are radians. There is a maximum limit for slope for any loaded beam. So there is a maximum limit for slope for any loaded beam. This is the slope or definition. It is the angular shift at any point of the beam between no load condition and a loaded beam condition. So the deflection is, it is the vertical shift of a point on the beam between no load condition and a loaded beam condition. In previous case, so this is angular shift. So like this, so the beam is bended like this, so the angular shift is theta. But vertical shift is, that is deflection, y or delta. So its value is different at different points on the length of the beam, and it is represented by y or delta. Its units are mm. The theta is radians. Already have discussed here. The units are radians, and then these units are in mm. So theta is radians and delta is in mm. So there is a limit for maximum deflection for any loaded beam. But in previous slope condition, there is a maximum limit for slope, and here also limit for maximum deflection for any loaded beam. So the coming to the introduction part, whenever a cantilever or beam is loaded, it deflects from its original position. Already I told you. So this is a cantilever beam. So the beam is deflects like this. So the amount by which a beam deflects depends upon its cross section and the bending moment. The cantilever of beam is loaded, it deflects from its original position. But the beam deflects or depends upon its cross section and bending moment, the amount, how much it deflected. In modern design offices, the following are the two design criteria for the deflection of a cantilever or a beam. In design of a beam, two design criteria are there. So one is on the strength basis and stiffness. So whenever the cantilever beam is loaded, it deflects from its original position. The amount is depends upon this cross section and bending moment. So you will learn in design of machine elements when design of a shaft, you will study the strength based design and stiffness based design. So whenever the cantilever beam is loaded, it deflects from its original position. Already you know this this part already we have discussed. As for the strength criteria of the beam design, it should be strong enough to resist bending moment and shear force. So whenever the beam is designed on the basis of strength, that beam should be strong enough to resist bending moment and shear force. So as per the strength criteria of the beam design, it should be strong enough to resist bending moment and shear force. Or in other words, the beam should be strong enough to resist the bending stresses and shear stress. It can withstand the bending stresses and shear stresses. And as for the stiffness criterion of the beam design, which is equally important, based on the whenever the beam is designed based on the stiffness, it should be stiff enough to resist the deflection of the beam. So when the beam is designed on the basis of stiffness, the beam should withstand, it can withstand the deflection of the beam. So in a strength basis, it can withstand the bending stress and shear stresses. This is the difference between this strength basis and stiffness based design. So in other words, the beam should be stiff enough not to deflect more than the permissible limit. So it will deflect up to certain limit, that is permissible limit, under the action of the loading. Not to deflect more than the allowable limit. So in actual practice, some specifications are always like to limit the maximum deflection of a cantilever or a beam to a small fraction of its span. See here shown beams, the beam position before loading, the simply supported beam. The load is acting at its mid span. Two supports are there. the beam position after loading, it bends like this. This is the deflection of the beam. How much deflected this one? This is y or delta. So how much twisted? That is difference to this point. This is angle. That angle is theta. Is different throughout its length. Here one theta 1, theta 2, theta 3 like this. There is a maximum limit for slope and there is a maximum limit for deflection. So consider a beam AB subject to a bending moment. As a result of loading, let the beam deflect from ABC to ADB. ABC to ADB. Okay? So ABC point say ABC to ADB. So initially the beam is ABC into a circular arc as shown in figure. So the length is L by 2 and L by 2 and the angle is theta or I. So let length of the beam AB L and M is the bending moment and R is radius of curvature of the bent of beam already shown in figure, the R, and I is the moment of inertia of the beam section. E is the modulus of velocity of a beam material and Y is the deflection of beam, that is CD. C to D, that is deflection Y or delta. The deflection from ABC to ADB. I is slope of the beam. I is slope of the beam. I or theta. So from the geometry of a circle, we know that AC into CB. AC into CB is equal to EC into CD. So now take AC into AB, CB. AC is L by 2. The total length is L and L by 2, L by 2 and the EC is 2R minus Y and CD is Y. EC is 2R minus Y. The E to C. The total radius is 2R, the diameter, minus Y value. So after simplification, you will get the Y is equal to L square by 8R. Why? Because we are neglecting the Y square. For practical beam, Y is small. So that's why Y square term, the deflection is very small. So you can neglect. So neglecting Y square term. So we know that the loaded beam M by I is equal to E by R. This is bending equation. Already we have discussed in previous sessions. R is equal to EI by M. The bending equation already know M by I is equal to sigma by Y is equal to E by R. you have derived also. So now write down the R is equal to the radius of curvature is equal to EI by M. So now substitute the value R in this equation. So R is equal to EI by M. So now we got equation y is equal to L square by 8R. So now substitute L square by y is equal to L square by 8R. In place of R, substitute EI by M. So you will get E L square by 8EA. So this equation gives the central, the second equation, gives the central deflection of a beam which bends in a circular arc. It gives the central deflection. So from the geometry of the figure, we find the slope of the beam. That is I at A or B is also equal to angle AOC. What is the angle at A or B? What is the angle I or at B? And AOC. AOC. This is I and C. Okay. So now, from the diagram, AOC sin I is equal to AC by OA. AOC. I. So AC by OA sin I is equal to L by 2R. Since the angle is very small, the I is very small, sin I may be taken equal to I, that is radians. I is equal to L by 2R radians. Again substituting the value of R in equation 3, L by 2R, in place of R is equal to, EI by M. R is equal to EI by M. So substitute this R in this I equation, you will get ML by 2E L radians. I radians. ML by 2E I. In this equation, note down these 2 points are very important. The above equations for deflection y and I, that is slope, have been derived from the bending moment only. So that is, the effect of shear force has been neglected. We are not considered shear force. Only the bending, we have taken the bending moment equation and then we have calculated the deflection and slope. The I, you will get here sin inverse L by 2R. Or sin I may be taken equal to I. Okay. So this is due to the reason that the effect of shear force is extremely small as compared to the effect of bending moment. The shear force is very small, extremely small when compared to the effect of bending moment. So in actual practice, the beams bend into an arc of a circle only in a few cases. So a little consideration will show that a beam will bend to an arc of a circle only if the beam is of uniform cross section, or in other condition the beam is subjected to a constant movement throughout its length, or the beam of uniform strength. In these 2 conditions only, there is possible the beams bend into an arc of a circle. So one is the beam is of uniform section, or the beam is subjected to constant movement throughout its length. These two points are very important. The equations, the deflection slopes have been derived from the based on the bending moment only. See, the beam bent into an arc, the diagram shown here, PQC. The beam is bent like this in a circular arc. Take the elemental length dx and dy, and the elemental the slope is d psi. Since in this, from the geometry of the figure, we find that the angle PCQ is equal to DC. PQC is equal to d psi. So ds is equal to r into d psi, and r is equal to ds by d psi. R is equal to dx by d, considering dx is equal to ds. So here 1 by r is equal to 1 by r is equal to d psi by dx. We know that if x and y be the coordinates of point P, then tan psi is equal to dy by dx. And x and y be the coordinates of point P, tan psi is equal to dy by dx. So from this diagram, you can write tan psi is equal to dy by dx. So from the geometry of the figure, we find that sin since psi is a very small angle, therefore taking tan psi is equal to psi. So here 1 by r is equal to d this psi by dx. The bigger psi, dx square by y is equal to dx. So we also know that the bending equation m by I is equal to e by r. So now write down the bending moment equation. M is equal to E into I into 1 by R. Here substituting 1 by R. 1 by R is equal to d square y by dx square. So now M by I is equal to EI into d square y by dx square. This is the bending moment of this geometry. So here we have calculated from this diagram. So in actual practice, the beams bend into an arc of two cases only. One is the beam will tend to an arc of a circle, or the beam is uniform section and the beam is subjected to a constant movement throughout its length, or the beam is of uniform strength only. Then only the possible of beams bend into an arc. So otherwise it is not possible. So from this diagram, what we have did, we have calculated the d psi or moment, the deflection equation, that is. See here, the PQC geometry, the small portion we have taken here. So in this, the length is dx and the deflection height is, the deflection is dy, and d psi is the angle. So at the P point, the P and Q coordinates already mentioned here. if the x and y be the coordinates of point P, at the point P, the x and y, at the point P, the x and y are the coordinates. So x coordinate and y coordinate. So here y coordinate is dy and x coordinate is dx at this point. So that you can write tan psi is equal to dy by dx. At this Q point, here also dx and x and y, but here the psi plus d psi. They shifted the position, the deflection position, and then slope deflection, the slope point. So that the PCQ, angle PCQ is equal to d psi and ds is equal to r into d psi. Here r is equal to ds by d psi or dx by d psi. ds or ds. So now write down the tan psi is equal to dy by dx, and then from the geometry you have find this psi value is a very small angle. So you can write 1 by r is equal to d square y by dx square. 1 by r is equal to d psi by dx. So we know that the m by I is equal to E by R, the bending equation, the bending moment, and I is here moment of inertia, and E is the modulus of velocity, and R is the radius of curvature of the beam. So M is equal to EI into 1 by R. So here R already you are written like this. Now substitute in place of R d square y by dx square. So what is d square y by dx square? R. Otherwise you can write M is equal to EI into d square by dx square is equal to d psi by dx. Is equal to EI into d square y by dx square. Okay. So now you can write M by EI is equal to d square y by dx square. M by EI into E is equal to d square by dx square. So this is the equation, slope and deflection equations of a beam for UDL. The slope and deflection of beam for a UDL. So these two are different here. Okay. Like this, you need to calculate the deflection slope of a given beam. So these are the references I have taken for this PPT. S. Ramamrutam. The author name and title of the book is Strength of Materials. Publishers are Dhanapati Rai Publishing Company and R.K. Rajput, author, and Strength of Materials title of the book, and R.K. Bansal, the textbook of Strength of Materials, the title. Publications are like me, publications. And R.S. Kurmi and Gupta, Strength of Materials, and publishers are Ashant and Co. So take any latest edition reference out of this for further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.